I just said we're rating greater than 6, then I'd only have to go to Tokyo to be able to do the query. So that's stuff you can do. And if you had a situation in which the SID and the rating were stored at Shanghai, and the name and the age are at Tokyo, and the TID or whatever I'm using, maybe the primary key, are stored at both, then I'd have to be able to construct the query by putting the pieces of these things together. And there is another approach that we talked about with replication. If sailors, suppose that we have a table that changes very, very infrequently. We talked about this with the broadcast join kind of approach, where you might store things at multiple sites or ship things to multiple sites. So suppose that sailors is something where the list of sailors does change. It doesn't change very often, and sailors is relatively small, whereas reserves, ends up being bigger. I might go ahead and store sailors at 2 or 3 or 17 different sites. And what do I pay? I pay the cost of having to replicate it at all the sites and having to play with the synchrony issues that are involved in doing that. And what do I get? I can do queries locally rather than having to do things across multiple different sites. So there are trade-offs that are involved in that, and again, there are consistency issues. Then there's doing joins. So again, if I have a situation where I want to go ahead and I have my sailors are located, this is silly, but example. Sailors are in London, the table, and reserves are in Paris. Sailors is, remember, 500 pages in our example. Reserves is 1,000 pages inside the example. What I could do if I'm trying to do a join is I could do a block nested join with sailors as the outer, and end up putting the result together. Where D is the cost to read or write a ship page, D stands for write a disk page. S is the cost to ship a page. It doesn't stand for sailors, sorry. It's the cost to ship a page. So I'm going to have my 500 accesses because sailors is going to be local. And then I can go ahead and read all of my reserves pages from the disk, which might end up being 1,000 pages. So I read them and I ship them, and I ship everything over to London to be able to do it. So that would be the cost of doing that. But if the query was not asked for at London, the query was asked at New York instead of London, then I might have to go ahead and see what I could do by shipping everything to New York so I could do the query. Or what I could do is I could execute the index nested loop join or whatever loop join I'm doing at London and then ship the answer back to New York. So basically, everything that we've talked about with optimization and different plans, in a distributed environment, you can execute all these different locations. And you can execute at even a third location, not even where the data ends up being stored and spreading things around. So all the things we've talked about with optimization and parallelism, variations of it show up in the distributed case, because again, it's more complicated to figure out how you ship everything around. So all this stuff ends up being dealt with, and you can ship things, you can ship everything, you can ship things on demand. There are lots and lots and lots of different approaches. It ends up being complicated. Another thing you could do is just ship the entire reserves table to London, and then do the execution size, and then ship the result to where it needs to be shipped, the result to New York. And by the way, if the result is going to be big, and you have to estimate what that is, it might be better to ship the 2 tables to New York, do the query there, and then have the result created inside New York. So again, there are many different ways that you can do this. All the things that we've had before, only multiplied out with all sorts of different awesome possibilities. There's another wonderful approach which is called a semi-join, which is a lot like an exists query. And you may remember we talked about semi-join inside 180, and semi-join is actually something that is used in practice. So remember, before, again, we had this query where we were trying to do a join between sailors and reserves. What you can do is the following thing. What you can do is you can figure out what your list of sailor IDs is. You're not shipping all sailors to Paris. You're just going to ship the IDs of the sailors. And maybe you had a query where you only wanted the sailors where rating was greater than 5 or something like that. So you ship only the sailors where the rating is greater than 5. okay? So what you then do is you join that together with reserves. So maybe there's a predicate on reserves where the date is, in July or something of that sort. So you take the set of sailors that satisfied whatever predicate you had on sailors, and then you shift that over to Paris, which is where reserves is. And you figure out the join of the sailors that you have together with reserves. Now, there may be all sorts of other predicates that are involved with this that show up involving reserves and sailors. But then what you're going to do is you're going to figure out which reserves, because all you shipped was the things which was the sailor projection. You get a reduction of reserves. Basically, what are the tuples in reserves that might be matches? What are the tuples inside reserves that might be matches? Not everybody in reserves is going to match one of the sailors that we care about. So we figured out which sailors we care about. We figured out which reserves correspond to those sailors, and we shipped that back to London. So we've got a reduced version of reserves. We haven't shipped all reserves. We just found the part of reserves that is potentially relevant for this query. The part of reserves that corresponds to the sailors that we're going to be looking at. We will ship that to London, and then we will join that reserve. So we trade off the cost of computing and shipping and compute, and we do an extra operation to avoid sending as much data along. We did the extra operation of figuring out which part of reserves is relevant for the sailors that we care about. And we shipped that along. That's an extra operation. To avoid having to ship around irrelevant tuples. Instead of shipping all of reserves to London, we're going to figure out which parts of reserves matter for the sailors we care about. So if there's a selection on sailors, and we want to get the answer in London, and we only wanted to be able to look. It might have been something where rating greater than 5. It might have been something where, we figure out we only want sailors whose name is Smith. So we figure out the TIDs, the SIDs of sailors whose name is Smith. 12 sailors whose last name starts with Smith. We only get the reserves that correspond to that. So that's again a way of doing what's called a semi-join, only matching, finding the things in reserves for which there is a match, which again is a semi-join thing. It's not like exists. Only finding the things inside reserves which correspond to a sailor that we care about. And again, that's an idea as well. And there's a fascinating heuristic which can have some false positives called a Bloom join. Bloom join is a lot like semi-join, only not as precise and not as expensive. There's a trade-off. Do you want to be more precise and more expensive? Do you want to be less precise and less expensive? The idea of the Bloom join is what you do is you figure out things where you compute a signature, a hash value corresponding to the SIDs that you care about. So you only care about the SIDs where the rating is greater than 5. And there might be 12,000 sailors whose rating is greater than 5. Here's the gimmick, and it's going to remind you a whole lot of what we did with hash join. I'm going to compute a hash value for each of the SIDs that I care about. Now there are puns, not mine, but there are puns from hashing. Because you're only going to go ahead and you're going to get a hash value between 0 and k minus 1, k different values. Say 128 bits, so there'll be 128 different values between 0 and 127. And every time that there's a sailor ID, there are 12,000 sailor IDs, every time there's a sailor ID, I will set the bit inside this 128-bit value. I'll set the bit to 1 that corresponds to that SID. There were 12,000 different sailors, there were only 128 bits. Puns have to be there. 12,000 divided by 128 isn't 1. Even if you're lucky, they're going to be puns. But what happens? The bit is set to 1, if there's a match. And now you know what I do over in Paris with reserves? I only have to ship over 128 bits. That's dinky, not a big deal. I will find the reserves which match based on this hash bit bloom filter. Now, will there be false positives? Meaning, will I sometimes find a reserves for a sailor that doesn't exist in London that I care about? Yeah, because there are puns. I set the bit 1, and it basically says everybody who hashes to that, I'm going to view as potentially relevant. And there will be false positives because, again, a lot of different values hash to bit 73 that are not values I really care about. But there won't be any false negatives. What do I mean by a false negative? If there's a reserve that corresponds to a sailor that I care about, the bit will be on. Because I set the bit because I cared about the sailor, about that sailor ID. So the bit will always be on if I care about the sailor. I care about that SID. But the bit might be on even though I don't care about that particular, because a lot of different values hash to the same bit. Now what I'm going to do then is send the reduction of reserves that correspond to the bloom filter. There will be false positives. I'll be sending across things that I don't give a darn about. What can you do with a drunken sailor early in the morning? I don't care about that sailor. But there won't be any false negatives. If I care about the sailor, the bit will be on. So I will ship the reserves that correspond to the bloom filter back to London. And then I will do the join. Possibly saying, oh, you sent me some junk, I don't care about that. But I won't lose anything. I may have some extras, but I won't lose anything. And I'll be able to do it. Now, what did I get and what did I lose? I only had to ship 128 bits. Well, I had to calculate the 128 bits, but it's just scanning through and setting the bit in the bit vector. But I only shipped the 128 bits rather than all the sailors that I care about. A little more work, a lot less shipping maybe, and the possibility of having the false positives, but no false negatives. Trade off all the time. Okay? So the bit vector is cheaper to ship than the semi-John projection, and it tends to be pretty effective much of the time. You could be unlucky, but on average, it's going to be reasonable. It's a trade-off. How do you pick 128 bits and all the rest of it? Engineering is fun. Have to pick reasonable values. And now, we're going to go ahead and look at cost optimization in a distributed environment. There are many, 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 many different plans. We've talked about all the different plans and the complexity of doing optimization when you end up having even just, your 3 or 4-way join in a single location. When things are distributed all over the world or all over a whole bunch of different locations, even if it's just inside a single country, it ends up being complicated. First of all, you have to count the network costs. And again, network costs have gotten a lot cheaper over the years than they used to be. They're still non-trivial. So it used to be you would focus on, disk costs. There was a long time where if you have a network issue, the network costs end up dominating. At this point, again, you can assume that most things are going to be in memory. Network costs have gotten a lot cheaper, but costs have to be dealt with. So communication has to be considered. You have to recognize that if I'm going to be a global optimizer, I can't tell the other sites what to do. If I have a homogeneous environment, I may have a pretty good idea of what kind of plan they're going to generate, because they're my brothers, they're my siblings, they generate plans the same way that I do. But I'm guessing on what a good plan is, and I'm making assumptions about what plan another site is doing, which may or may not be perfect. Every site gets to do its own version of optimization when it gets queries. And again, there are all sorts of other methods that can be used to do the joins across different sites, including the ones that we just talked about with the semi-join and the bloom filters. So the query site constructs, they suggest a global plan. It may have suggested, local plans that it's thinking about doing, and it may even, be able to tell the other sites, especially if it's homogeneous, what it thinks the thing is. And the trouble is that sites may they may have different statistics. The statistics, remember, we're not going to keep the statistics completely up to date locally. And we darn well are not going to be keeping the statistics up to date globally. So there are all sorts of different things that maybe, besides there may be a new index that was created at the local site that this other site didn't know about, or there may be an index that got wiped out. All sorts of different things can end up happening. And so basically the assumptions a global optimizer makes about the local site may be wrong. The local site can end up making decisions. Again, I will emphasize the way things are mostly done now, there are things where you try to take advantage of things like microservices or individual site services. The trend has been against doing a lot of stuff involving distributed database. Question?
So communication, you said that communication costs have gone down. Is this because the network has just gotten better, or is it because there's now a specific protocol in networking that allows
all the above. It's because the networks have gotten lots and lots faster, and it's because there are lots of clever algorithms that have been designed to be able to do those faster networks and avoid things like blocking and network disruption of various sorts and all the rest. It's because you also have n different lines between things. It's not just that networks are faster. You've got lots and lots and lots of lines between things, both for availability and for performance. You ever heard remember I told you that the word partition tended not to be used when you talk about splitting data up because there were network partitions. If you have an environment in which network partitions are possible now, you have a really badly designed system. Yes, enough bad things can end up going wrong that things could theoretically break, but you're going to have, it's going to take n where n is large different failures to be able to have things that are not connected. Things could slow down if you end up losing a lot of your bandwidth, but you're not going to have something where you just have one way of getting from A to B. Not only can you go from A to C to B, but you're going to have lots of different ways of getting even between A and B. You don't want things to go down. You don't want your business to go down. It's not that expensive anymore, and the speeds are high. And again, the cost to your business is your data, and your business is your management of your data and supplying of your services to your customers. Data doesn't go down. It still does happen. Mostly it happens because of software bugs. Mostly it happens because people upgrade and get things wrong. So, by the way, just as a fast aside, a typical approach to upgrade, including lots and lots of testing before you do it, is called the canary in the coal mine approach. The basic idea on that kind of approach is you go ahead and you experiment on, say, 1% of your customers, maybe less than that, with a new upgrade. And you only do things where you can go back to the old software if you have to. And if things work well in terms of function and performance and availability and so on that 1%, then you might go up to 2%, 3%. But if you have problems with 1%, you hardly go back to the old version of the software. You don't let the other 99% of your sites or customers see the problem. And again, there are all sorts of other variations, clever things about how that ends up getting approached. You've heard the term DevOps, which basically talks about development and operations. Operations and development are not separate things done by different groups these days. Operations tends to be done by the same group that does the development, and when they develop the operational things that are associated with it. It's not a separate team, it's not a separate function. You develop it to be able to work in an operational environment. And the changes often get made, n times a week, n times a day. All sorts of things end up getting upgraded. And the rule, for example, that used to exist at Facebook was, basically work fast, break things. And they put a caveat on that, which is except for infrastructure. So they still try to work fast, and they sometimes break things, but they tend to be more careful about things where it's an infrastructure, it's an application, then you bring down the application for a little while, and you do the canary in the coal mine thing that I mentioned. But if it's an infrastructure thing and it's going to take down Facebook completely, you try to be a little bit more careful about it. You try to make sure that there isn't something that will take care of Facebook completely, take it down. Replication. Okay, if you basically, if you go ahead and you do a transaction, then one of the ways of dealing with this is the one that I mentioned before. All the different copies of the data have to be updated before the transaction can commit. That has this minor disadvantage that, again, one copy is down, you can't do your transaction. That's not what you're trying to go for. So again, that's transparent. So, and if you have asynchronous, then you only, periodically update. You may say things may get out of sync, in which case you have to know I'm dealing with a copy that was good as of an hour ago, but it may not be good now, and that has an effect on how applications are written or what sort of, results that you follow with your consistency. And there's an approach that I'm gonna mention. I don't have that much time, so I wanna mention this right now. How many of you heard of Thomas's rule, otherwise known as R plus W greater than N? Nobody's willing to admit it. Here's the general idea, and I'm gonna give you a simple example. Suppose that I have N sites, and I wanna make sure that I always have consistent data. There are people who violate that, just as there are people who run just review committee. But what I wanna be able to do is the following. I have my 5 sites. Whenever I do a read, I will read 3 of my sites, and I'll always be able to tell the latest version. So the 3 sites may have different data, but the version values are always going up, so I'll be able to figure out what the latest version is when I read. When I write, I'm gonna write 3 places. And again, I'll write the new version number. Versions are always increasing. When I read, I always get what the latest version is. When I write a new version. I always read 3, I always write 3. If I have 5 things and I take the intersection of 2 sets that have 3 things in them, what's the property that I must have true? They must intersect and have at least one thing in common. If I read 3 things, I must be reading one site that has the latest copy. Because if I'm reading a site that doesn't have the latest copy, there can only be 2 sites that don't have the latest copy since I read 3. So because I'm writing 3 and I'm reading 3, I will always be able to get the latest copy when I read. I could also play this game with, let's say, R equals 2 and W equals 4. Intersection of a set of 2 and 4, if there are only 5 copies, I must always be able to read one site that has the latest copy, so I can tell which is the later copy because the versions are always going up. Aspects of locking that I won't go into on that. Just think about shared locks and exclusive locks as a way of thinking about it. That's Thomas's rule. That's the R plus W greater than N. In that environment, even if I end up having sites go down, I can still read and write. If one of the sites is down, I will still be following. Suppose that one of my sites is down, and suppose I'm playing my game with R equals 3, W equals 3, and N equals 5, and then one of the sites goes. I can still play my 3-3 game. It's maybe going to take a little bit longer because some of the sites might be further away. And also, by the way, I'll bring back a new site that has the current data on it. I'll try to bring that back pretty quickly so that I'll get back up to 5. So I can still tolerate a failure in the case that I described. In fact, I can tolerate 2 failures because I'll always still have 3 if 2 things fail. And I'll always be able to read 3 and write 3. Again, may take a little bit longer, but again, failures aren't that often, but I will try to bring something back in case there ends up being a failure so that I can end up proceeding. So here it is. Voting. A transaction must write a majority of the copies to modify an object must read enough copies to be sure of seeing at least 1 copy. So for example, in the case where 10 copies, following the rule I described, suppose you write 7 and you read 4, R plus W greater than N, the R set and the W set must intersect. I'll always be able to read the most recent version. Okay? And because reads are common, I usually won't want to go ahead and read 4. I want to go ahead and play another game, with the number of things I have to read being smaller often, so the number of sites I try to read might be 2 or something like that. I could do something with read any and write all. The trouble with that is if I'm having to write all, then I have a problem. If read 1, in this case, has a problem because I'll have to write 10. That's not good. There is another game which is typically write the primary. There's a primary carrier, write the primary plus enough other copies to make a majority. So again, if I'm working with R plus W is greater than N, I will write to my primary, and I will only read from the primary, because the primary will always have the current copy. That works very nicely as long as the primary doesn't fail. So I'll have to have something where there's a situation where if the primary fails, somebody else takes over as primary. Details I'm not going to go into, but basically the technique that says I only read from the primary, and as long as the primary is up, and I will write to the primary plus A enough to make a majority. So in my case where N equals 5, I'll write to primary plus 2 others. And that will all work, and even if the primary fails, things will end up being successful as long as I can elect a new primary, although setting up a new primary so it has the current data is a pain. There are lots of different variations of that. We will go over this. I'm out of time. I told you I doubted I would be able to finish this today. I will finish this next time and possibly get started on one of the other 2 things. I will tell you, by the way, let me warn you about something in advance. I will be talking to you about 2-phase commit next time, which, by the way, also comes from Mohan and Lindsay. 2-phase commit has nothing to do with 2-phase locking, except that they both have 2 phases. I don't want to be 2-faced about this. I do want to be 2-phased. I don't want to phase you. But we will be talking about 2-phase commit, and again, do not confuse that with 2-phase locking.